the relation y is the absolute value of x cubed over 3. It's that curve. Okay? So having full throttle either way will force me to live on that curve. So in exactly time t, y, and if I do full throttle, in exactly time t, if you want x to be the maximum, then y is dictated. I don't have any freedom for y. This is the y that I will reach. So if you're asking, can I reach a point that is less than this value of y, it means that you must give me some freedom in this. X cannot be t, x can be somewhere here. Okay? If x is somewhere here, can I reach value that is less than this curve? This is the question. Well, what's the big picture? What you're trying to do? I'm trying to get the reachable set. And like any set, I'm trying to get, in the 2 dimensions, I'm trying to get the right boundary, left boundary, bottom boundary, and upper boundary. Okay? So this is obviously the right boundary, because it's maximum x. Left boundary, maximum in negative. I'm trying to get the bottom boundary. It seems that this is also the bottom boundary, because they close from below, but I'm not sure yet. Let's check that. So let's ask the following question. If you give me some value, final value for x here that is less than t, because if it's equal to t, no more freedom, it's less than t, can I get y that is below that curve? Let's study this in just one line. That's easy. It means that your u is not full throttle, it's just some r that is less than 1, right? Okay, so this means that x, please integrate x dot equals u, so this is rt, so y dot is r square t square, so this is means that your y is r square t cube over 3, so y as a function of x is 1 over r x cube over 3, okay? And this is the value that is given by the curve. So you can multiply by 1 over r, and r, we said r is less than 1, so this is larger than 1. So you can never have a value that is lower than this guy. This is indeed the lower boundary. But at the same time, it tells you that you can achieve higher. Okay? You can achieve higher. Can you tell me what is the maximum? So for a given thing, let's say t is 1 second. And I'm telling you, okay, in 1 second, I want the final x to be half, and I want the maximum y. So here, half, I want the maximum y. I can't get below that curve. Can you go higher? Yes, for sure. By how much? I want now to construct the upper bound. What's the maximum y? Okay? This is not a trivial problem at all. And I'm going to do some digression here. This is on a side. I'll come back to this problem again, and this is digression on optimal control. Okay? How many of you have studied or is studying optimal control? 274. Okay, very good. Very good. So what's optimal control is about? Let's see, it's not x dot, we have a very generic differential equation. It's not even affine control, anything, f of x and u, okay? And I'm putting arrays means that they live in Euclidean space. X in Rn, and u is in Rn, okay? And we want to answer the following question. So the optimal control is to answer the following question. Find u, say that maps from 0 to t, whatever, to u in Rn. So you can have control bounds, very fine, that's okay. That steers your system from x naught, some given initial condition, to some given final condition, and minimizes some cost function integral from 0 to t f naught any generic function of x and u dt. Let's be a little bit more precise. This is x of t, u of t, dt. Knowing that these guys can be free. Can be free. What do you mean? So you can specify the entire states and the initial condition, final condition, that's fine. Or you can say, okay, I want to steer from here and over there. No, I don't care. I don't care where is the end point. Or I care about half of the states to be exactly these values and the other half, I don't care about their values. Actually, the same for the time. The time also can be free in the sense you don't know when you're gonna reach. Can be free. So you don't have a requirement for the final time or the final point or the initial point. The setup of the problem is quite generic. This can also admit some time variation here. It's a very generic principle. This is a typical optimal control problem. So if you ever encounter the problem like this and you want to solve, go and read some chapters in optimal control. You will solve it for you. And the principle that we apply is Pontryagin maximum principle. So this is what we have on our first lectures in optimal control theory. It's the Pontryagin maximum principle. You can say it's the strongest principle in control theory, modern control theory. This is the typical problem. Look at our problem. We have x dot equals u, y dot equals x squared, right? So this gives you dynamics, f of x and u. And we want to find u 0 to t to negative 1 and 1, right? That steers the origin to where? Some x final that is less than t in our problem, right? And the y is actually free. I don't know y a priori. I want to maximize y. So I don't know that the final y. I'm not specifying. If you're specifying it, you're not maximizing it, right? I don't know what's the maximum, so this is free to me. And I want to maximize y, right? This is my objective on a side here. I know that y, the final y of t is the integral of 0 to t of y dot dt, right? By definition, fundamental theorem of calculus, right? And this is what? Y dot is x squared. So actually